Mark to become a radio operator.
Especially when I'm
Yeah, oh. Lock the doors.
Doing wandering again, is he?
All right, good afternoon, everyone. Welcome. I'd like to start by acknowledging the traditional custodians of here on the Gold Coast, the Yagambah people. Housekeeping. Tonight's event is today's event being live streamed. It means faces and voices from the room may appear on the website and for promotional materials on YouTube and Facebook. There is a camera at the back of the room, so we'll get the back of your heads. If you walk in front of the camera, then Oh, okay. Oh, thank you very much. Sorry. Okay, so we do this to share what we're doing to a wider audience and help promote the club, so more people can get the value of amateur radio. I'd like to remind everyone to please sign the register before you leave. It keeps track of for insurance and club records. Speaking about being involved, if you're not already a member, membership forms are available. Joining helps support events like this and keeps the club strong for the future. Fees are to see me presentation. And don't forget, after the talk, we'll be throwing up the barbecue. Now, on to after this morning's talk. It's my pleasure to introduce Ron Bertrand. He will be speaking on what is radio. This is more than just radio's day-to-day. Ron will be looking at the many applications of radio we don't always think of as radio. Touch modern communication techniques such as BPSK, QPSK, and QAM, and even what Fourier Transforms has to do with all this. Please join me in welcoming Ron.
Thank you very much. What I'm hoping to get done today is a little bit of history on radio and some of the modern methods of communication. One called QAM, which is in the advanced syllabus now, so it will be an exam soon. And the other thing is called Fourier Transform, which is also in our syllabus. It's very mathematical. We don't know any of that. We just have to know what the Fourier Transform is used for and a little bit about it. But what I might do to start off is ask you the question, what's radio? You're all radio amateurs.
Communication device.
What?
Communication device.
So that's a telephone.
Yeah.
Can we narrow it down a bit more? What is radio?
Communication device utilizing radio waves.
Oh, radio waves. What are radio waves?
Electromagnetic radiation frequency.
How about electromagnetic radiation?
Yeah.
Radio waves are electromagnetic radiation, which are basically sine waves. And if we want to transmit some information to somebody else, we need to erase that information on that sine wave. And then we need to radiate that sine wave. We have to receive it to modulate it. So if we had a sine wave, and that's a single sine wave. You've got to think maybe carrier wave. It could be 1 megahertz, 10 megahertz, 100 megahertz. But I'm not going to draw 100 cycles per second. So is carrier on that. We could change, so we could increase the amplitude modulation. Change the frequencies to represent different values. That could be pretty. So we've had amplitude, we've had frequency, and phase. So if we could change the phase of this, for example, if I change the phase of this by 180, we'd have that. So now you've got two signals, the blue one and the red one. The red one could represent a 1, and the blue one could represent an O, and we can toggle as quick as we like between those two frequencies to transmit 1s and O's.
It becomes digital, doesn't it?
It's using electromagnetic radiation and putting information on that electromagnetic radiation to have it received at a distance. How fast does it travel? Light speed, how fast is that? 180, something like that. I haven't heard that for a while. 300 millimetres per second. What about this? What if I had a microphone and a microphone amplifier, and I put it onto an antenna? That seems like an easy way to do it to me. We haven't got to muck around with RF amplifiers and BFO. We just go straight from the microphone to an amplifier, straight to the antenna. Would that work? No. Why not?
There's a secret on it.
Why would it work?
The sound deteriorates too fast.
Say again?
Sound deteriorates too fast.
But well, I'm wanting to transmit electromagnetic radiation, not sound.
You need a transmitter.
Say again?
You need a transmitter.
Is it that transmitter?
No, that's necessary.
Why do you think that one radio? Aidan?
Because audio frequency size.
Okay, well, let's say we were transmitting 10 kilohertz. Yeah. So we're putting 10 kilohertz in the microphone transmitting. And let's say we wanted to find the wavelength of that. Because we're not making an antenna,
That's
right?
a couple of feet.
So wavelength equals the speed of light, 300 millimetres per second. In this case, divided by 10,000. So we can cross off 4 zeros there, cross off 4 zeros there. We need an antenna 300,000 metres long. I think they call that a telephone line. And it has been cover a little of technology before I. You week or two ago about there was a station And the reason for such a low frequency is that frequency will go underwater and follow the under the seabed. It's for communications and navigation of submarines. The antenna is down now, they've decommissioned it, but the antenna, which is approximately 500 metres. But that's not 300,000. No, it's 30,000, sorry. 30,000, yeah. 300,000 metres. So that antenna is far too short. I mean, it's really a lot too short, isn't it? Now, antennas which are too short have a reactance. They're not resistive, they have a reactance. If they're too short, that reactance is capacitive. Capacitive. Every short antenna is capacitively reactive. So if you build an antenna and it needs to be 20 metres long and you only make it 19, it's going to be capacitively reactive. And the way you defeat capacitive reactance is to add some inductive reactance. If the antenna is too long, it's inductively reactive. So you need to add some capacitive reactance. So at the bottom of the, I'll put the name of it up here. At the bottom of the Amiga station, there's some huge huts. And in those huts, this is an end-on view of massive loading coils. I've drawn them end-on instead of like that. Right? Massive loading coils. And the wire on them is about as thick as my forearm. But it's big, huge copper winding. And all that inductive reactance is to get that antenna to resonate at 10 kilohertz. And when that happens, it radiates. So you can transmit audio. I know all the books, except mine. I know all the books say you can't transmit audio frequencies, but you actually can. It just takes a lot of power. It used to run at about 100 kilowatts. And I take them around the world. And how they were used is every submarine knew where all the Amiga stations were. And you could judge by the amount of time the signal took to get to the submarine, so the submarine could look at 2 or 3 or 4 Amiga stations. The operator didn't have to do any calculations, the equipment did it for him. So if he turned the equipment on, it would give him his position in the ocean wherever he is.
Sorry, what era was this, Ron? Is this recent? Or?
It was decommissioned about 4 years ago.
Okay.
Yeah, like Exmouth, they're now rejuvenating.
Sorry?
Exmouth, they're now putting back together again.
Oh, really?
So on
Not-
WA,
Right.
which is a slightly different antenna array, but it's still BLA.
I don't know why they disbanded it, because it's an operating system, and if we ever have a war or something like that, we will be totally dependent upon the GPS. In fact, we're totally dependent on the GPS for a lot of things. The aircraft can't fly today without GPS. So I don't know, if something's working, why dismantle it?
They use a high guard rate system now.
But I'm going to go on a tangent here for a minute, because you mentioned the Gendelese over the horizon radar. So on not a good map drawer, that's the west coast of Australia.
Fair enough.
We've got over the horizon radar in Western Australia that the idea of over the horizon radar is it transmits a pulse. If that pulse of electromagnetic radiation hits an aircraft, you get a reflection, and you can see the reflection, and you can tell how far away that target was. And it relies on ionospheric propagation to get around the curve of the Earth. It's called over the horizon radar. Do you remember that Malaysian plane that?
Yeah,
Down here?
yeah. Well, no,
Well, I think they're pretty sure it went down there, but what, I've gone on a tangent here because it's one of my bugbears. Why didn't we see it?
It's not always on, isn't it?
Why isn't it always on? Like it's there. It's there to detect. It's there to detect incoming aircraft, and what they're going to do is no good.
Well, it's owned by the Australian government, so it was probably down for maintenance.
Yeah.
Well, I figure what might have happened is they might have seen it and didn't want to show their hand. Right? Let's not show our capability. Or they didn't see it because it was not working or not switched on. Either way, it's a bit embarrassing, I think.
It is considered one of, if not the best system like that in the world. I think the Canadians recently contracted Australia.
I don't know why.
You can hear that damn thing sometimes, say, on 27 metres.
That's a woodpecker. Well, woodpecker's not going
The
anymore.
one thing that's not been done.
The woodpecker is a Russian over the horizon radar.
Right, that is.
And they used to go tut, 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 like a woodpecker.
Yeah, I think this one is kind of, woodpecker is physically located now in
Ukraine.
Ukraine.
And it's,
Right next to a nuclear power station.
yeah, and it's dilapidated.
Yes.
It's dilapidated. Anyone who watches abandoned engineering would have seen the woodpecker antenna.
Doesn't the over horizon radar put a big block on your HF band, and it's a really deep, annoying tone that comes through?
It's a pulse.
Yeah,
It's just a pulse, right? And it's not supposed to go on over the band, but and ours doesn't. But the Russians really didn't care about that.
So what is lying on the top end of the 20 meter band?
I don't know.
Something that is for about 30 kilohertz wide.
No, I don't know what that is. So you can transmit audio. What we do as radio amateurs, if we want to transmit audio, we don't. There's a mic amplifier, we put a mixer in and an oscillator, and we transfer the audio to radio frequencies. So we mix the audio with radio frequencies in a mixer, and this goes out at 10 megahertz or whatever. And that's better for us because then we don't have to make really huge antennas. We can use smaller antennas. So regardless of how we've made our electromagnetic wave and how we've modulated, how does it transmit? How does it go? How does it leave you and go to you and you hear it?
RF energy.
So, sorry?
RF energy.
Yeah, but how does it get out of the antenna?
Marvelous. It's just a real wattage.
Is an antenna. So we're energizing it with, radio frequencies. We're only going to use radio frequencies if I don't want to draw huge antennas, so we use radio frequencies. The current will flow in the antenna in that direction first, and then it'll build up to a maximum, then it'll diminish, and the current will flow in the opposite direction. So the current in the antenna is doing that, running backwards and forwards. And what happens is that the current in the antenna creates an electric field. It creates a magnetic field too, but the magnetic field is in the board, so I'm just going to draw the electric field. So it creates an electric field which gets bigger and bigger. And then it changes direction. And what happens when it changes direction, the electric field then has to collapse back into the antenna. So it does the opposite. So the electric field has to collapse back into the antenna. So if the RF is fast enough, a high enough frequency, the electric field doesn't have time to fall back into the antenna. And what happens, it starts doing this. And eventually it pinches off and you get a loop of electric field in free space. It's a bit like a bubble pipe. Like bubbles on a bubble pipe. The bubble grows, disengages from the pipe, then the next bubble comes along and pushes the first bubble, and so on and so on and so on. So, you end up with a loop of electric field and a new loop of electric field being created. And those two loops repel each other, so this one repels that one at the speed of light, c. It's pretty simple, but that's how the wave gets out of the antenna. Meters per second. Why? Why does it travel at 300 million meters per second?
Because electromagnetism is light.
I don't know if any of you, what's Krauss, you know Lawrence Krauss, the physicist? He's a favourite watch of mine. He's the one who wrote the book, The Universe from Nothing, or something like that. So he was trying to explain how matter and material could just come out of nothing. But the problem is that there is nowhere in the universe where there is nothing. There is something everywhere. And if you go into space has two properties, and I'm talking about space out of the Earth's atmosphere. It wouldn't matter if you measured it in the Earth's atmosphere, it's about the same. But most of us know what permeability is. Permeability is the ability of a material like iron to concentrate a magnetic field. You know, if you make a coil, to create an inductor, that's permeability. If you want to create more inductance, you put an iron rod or a ferrite rod inside the coil, and that will increase the inductance. The other quality of space, these are qualities of space. You can measure them here too, they're easy to measure on Earth. The other one is permittivity. And permittivity is the ability to concentrate and a guy called James did this. He predicted would travel at the speed of the square root, and I won't use them here, of permittivity plus permeability. It's Picasso writing, I know what I'm writing. That's why light travels at the speed that it does. Because the universe in space has characteristics of permeability, and that's what those values were different. Then in the book, I've got the book here. Because you have permeability and permittivity in space, and because a radio wave, electromagnetic wave through space, I'm talking about somewhere away from the Earth, wherever the radio is, you've got instruments to measure. Excuse me. You can put instruments in space or on Earth, because the difference between doing the measurement and literally space is small. And you could measure as that wave is going back, and the current is that way. When you use a field strength meter to check an antenna to see if it's working, you're measuring the voltage. In other words, you can measure the strength of the electric and magnetic fields. And so if we say electric and magnetic fields, there is equals E over I. That means that space a lot of us are used to thinking about resistance and impedance as an object. A resistor has resistance. An antenna feed point has a certain impedance. But impedance can exist where there is nothing except an electromagnetic wave. So if we measure the voltage and current of any electromagnetic wave anywhere, and we get these two values, we come up with an impedance of 120 pi or 377 ohms. That means the impedance of space is 377 ohms. Now, as radio amateurs, you always try to match your transmission line, your transmitter to the transmission line, and the transmission line to the antenna. But now you've got to your antenna, right? And the load for the antenna is space. And the impedance of free space is 377 ohms. Is not that a mismatch? Isn't that a mismatch? It's not 50 ohms, is it? So your antenna transmitter is 50. Transmitter is 50 because we build them 50 ohms. That's the only reason why transmitters are 50 ohms, because the engineers that designed it said we're going to set it on 50 ohms because most radio amateurs are that lazy. I don't want to use coaxial cable. Again. Circuit. It doesn't matter because we're never going to reach the end. To find a shorter active circuit on an infinite line, you'll never get it because the line's infinite.
You never get anything returned.
You'd never get anything come back. That's the same as it is with free space. Even though there's an impedance mismatch there, 377 ohms, you're never going to get a reflection because it's never going to get to the end.
So that means it's a match.
It's a match. But it's not really a match, it just means it doesn't matter. It doesn't matter that free space has got that impedance. I'd like to talk about a little bit more of old technology before we move on. I was very lucky when I was a young boy because I got a job with the Postmaster Journals Department. Anyone remember them? Were you alive when they existed? I was. And my first day of real work, sitting in classrooms for a long time, but my first day of real work was at a television, because the PMG then used to run all the TV transmitters and all the radio stations. They didn't have, commercial radio stations weren't run by commercial people. They're run by the government. And my first posting was at Albury, actually 20 kilometres out of Albury, at a mountaintop called Mount Barramuda. And there, and in those days we only had two TV stations. The ABC and a commercial station. And they weren't on all the time. You know, the TV came on about 1 o'clock and went off at 10:30. Wouldn't be very happy to do that. So there was AMV4, that was the commercial station, and ABAV1 was the ABC. And each channel had two tracks. The same big here for that one. And they were combined and go down, and they were 100 kilowatts each. So you've got another set of two 100 kilowatt transmitters underneath them. And the reason why I mention this is radio receivers were so deaf back in the 60s, you had to have a lot of transmitter power to get a good picture. And the reason why you had two is so that if something went wrong with one of them, you could turn one of them off and fix it. Because if you turn one of these off, only a reduction in dB, 3 dB less power. And no one would notice if one of the transmitters you get we don't need to relate. So your total power being transmitted is 400 kilowatts.
Were they both in the same place?
Yes, yeah, a big room, and you can actually walk inside these transmitters. You can open a panel and go inside. You have to put your head down, watch all the high voltage, but you can walk inside. So, and the typical efficiency of any transmitter, including today, is about 50%. So in order to get 400 kilowatts out of the aerial, you had to get 800 kilowatts in. So the power into this station was 800 kilowatts. And when you add up all the that use capacity, you can round it off your if at Mount Tamworth, here, transmitters are kilowatt always why is that? And this machine stands for, so there's two states. So one phase is one state, the other phase is another state. And with BP, those phases It's called a diagram. We're doing it for and the other. And then there's there, there, there. So, 1, 0, 1. We can do something better. This is up to 6 QPSK. The symbols will go on the circumference. So if we went to overall spacing, too high, a digital technique. The B was going back to the BPSK, it just changed. You haven't seen that. This 180 degrees apart. So this phase, the phase to shift 180 degrees there. So the sine wave would be shifting 180, coming back, backwards and forwards 180 degrees. And also it was a symbol as a digital episode, and it gets noise on it. Get it off because it's very hard to detect in a sine wave. And what is this symbol? What is with all of this as well? Noise is a symbol. It's somewhere it should be, but it's still close up to where it should be. In the 1990s, there was a really big explosion in technology that I really think caught everyone a bit off guard, including myself. One of the things I noticed, because the internet started to rev up in the early 90s, didn't it?
The birth of the Commodore 64.
Yeah, I had a Commodore 64. Did anyone have a 2400 baud modem? Am I that old? Oh, thank you.
I've still got one that's 300.
Yeah, before that they were 300.
And that's an acoustic coupler.
I don't think they used on the internet. Well, when 2500 baud modems come on, I thought to myself, oh, that's good. And of course, these modems were using copper telephone lines. And copper telephone lines are extremely poor quality. Really extremely. When you join your coaxial cable and joins on the antennas and thing, you try very hard to keep the impedance the same. So if you've got 50 ohm cable and you want to connect it to 50 ohm cable, you use connectors that are 50 ohms. So there's no change in impedance. Because if there is a change in impedance, let's say that's 50, and you do a bludgy joint here in the coaxial cable, no, you don't need connectors, we'll just strip it back and twist it together, put a bit of tape over it. That will cause the signal to be reflecting. Won't reflect all of it, some will keep going. And Darryl, you're with Telstra, aren't you? You use a TDR? Yeah. What Darryl uses is a radio transmitter. It transmits a signal down there, because he might be trying to fix a coaxial line or whatever. And so you send a pulse down the line, and whenever it gets to an impedance irregularity, like that, it sends an echo back. So on a screen, you can see all the joints and bad spots in the cable over kilometres. And the problem with telephone lines, that's why I started that, is they're very, very poor lines. They're supposed to be 600 ohms. I doubt if that's ever happened. Maybe with the aerial, when they had aerial lines and they were spaced out in the open air, they might have been, but telephone lines are terrible. They're meant to transmit audio frequencies from 300 to 3000 hertz. That's what they were built for. Yet the early 90s, come on, the internet's here, and we've now got a 2400 baud modem. Well, you think, oh, that's probably in that band, you know, it's audio, it's not too high. What happened next? I think they went to 4800, no? Then 9600?
Yes.
And that's when I started to ask questions. How can you get that amount of data down a telephone line? Because it shouldn't happen, it shouldn't work. And it just kept going. They went to 22K, didn't they? And 48K. And then they went to ADSL on copper pairs. And we're getting 100 megabits per second down a telephone line. And if someone had said that way back in the 50s or the 60s, oh no, a telephone line will never transmit speeds like that. But it did. And at the time I asked all my IT friends, how does this work? How does it happen? How can you get so much data down a crappy copper pair? None of them knew, which didn't help me. But what it was, there were a couple of things. There was a new mode, and there's a whole lot of modes, by the way, but the one I'm going to discuss is the top one. Is the best mode for modulation you can get. And I'll tell you later how many things use this mode. And you don't have to understand the mathematics or anything like that. You just need to have an idea how it works. The mode is QAM. Most people just say QAM. And here's a constellation diagram. And what we're going to do now is create a symbol from a certain angle and amplitude. So that's the amplitude. The distance from the origin to there is the amplitude of the symbol. And the angle of the symbol is this angle here. And we could put for four symbols in there. So each of these symbols has an amplitude and an angle. An amplitude and an angle. So now we've got four symbols. So we could go 0, 0, 1, 1, 0, 1, 1. Notice we're not on the circumference anymore. When we're using BPSK and QPSK, our symbols are on the circumference of the constellation. But now not on the circumference anymore. This is called four-quant, obviously because there's four symbols. So all we're doing is taking our information and encoding it into these four symbols. So at the other end, you have to know what that coding is because you've got to decode it. But it could be voice, it could be data, it could be television reception, it could be optical fibre communications, it could be modems, the modem works with QAM. Unfortunately, there's not a lot happening in amateur radio yet with QAM. We're still playing around with FSK, which is frequency shift keying and phase shift keying, and combinations of them. But we're not really, in amateur radio, we're not utilising QAM. Yeah, it's in our syllabus. So if you went to 16 QAM, there would be four symbols in there. So we've got 16 symbols now. And we can keep going up and up and up and up. I've seen as high as 2048 QAM.
I think HDMI is that, the 246, 2046 HDMI. Yes,
Right.
HDMI. If you have a look at the diagram, the diagram of that, it's just like a mess of dots.
Yeah,
It's impressive.
There's a good diagram in the book. No, there is, most of what I'm talking about is in the book, but not. So that's what crime is. I'm not going to tell you how we generate it. It's too complex. And that's how those modems are able to go faster and faster and faster and faster because of QAM. I didn't tell you what it stood for. Quadrature amplitude modulation, which sounds like a mouthful. All it is, just remember, all it is each symbol, you don't have to worry about how it happens, is for QAM. Now analog signals are converted to that and transmitted as an analog signal. This is analog information. This is digital information in an analog signal. Because you can't get digital signals from the and this is the mechanism. Your digital TV that you watch at home is modems are quite. There was another, let's see if I can find when this guy invented this. Fourier, John Baptiste. I think it was around about 1822. His name was Fourier. Now radio didn't exist in 1822, but he worked out the mathematics for what's known as the Fourier Transform. And in 1822, it didn't have much of an application, and no one paid it much attention. But in 1965, two chaps by the name of Cooley and Tuckey wrote an algorithm to do the Fourier Transform. And what the Fourier Transform does is convert, and you'll have to let me explain this, I'll say it, and it might be double Dutch, but then I'll draw it on the board. What the Fourier Transform does is enable you to convert a signal that's in the time domain to the frequency domain. Let me draw a signal in the time domain. That's an oscilloscope. So an oscilloscope, and the horizontal axis is time, and the vertical axis is amplitude. So if I put a sine wave onto that oscilloscope, it will just draw a sine wave. That's pretty easy, isn't it? Everyone got that? What the Fourier Transform does is convert that into the frequency domain. And now, and by the way, that's a spectrum analyzer. If anyone knows what a spectrum analyzer is, they show signals in the frequency domain. So this axis here is now frequency, and this axis is amplitude. So if I had a 1 kilohertz sine wave, so just a sine wave at 1 kilohertz, there's nothing else there except 1 kilohertz, and I convert it into the frequency domain, I would see that, just a line. That's what the Fourier Transform does for us, convert, I haven't told you why yet. But that's what it does. It converts the time domain to the frequency domain. When you get a lot of complex signals, like most of our signals aren't just sine waves, they're hundreds of sine waves. Human voice is full of a huge number of signals. So when we look at our oscilloscope, it doesn't look like that. It looks like this. Right, it's everywhere. It's a mess. That's why we don't look at it. If we convert that to the frequency domain using the Fourier Transform, and you'll never have to use the Fourier Transform, we get this. In other words, we now get all, instead of this mess, we now get all the discrete signals in that complex signal in the frequency domain. Because we've now got the signal in the frequency domain, we can digitize this signal and analyze it.
Does it just like a waterfall?
A waterfall is a frequency domain. Yeah. But now that we've got it in the time domain, it's very, very easy to identify artifacts, bits, artifacts, which don't contribute to the intelligence. My wife says that to me a lot. Your artifact contributed to the intelligence. So what that means is we can eliminate, for example, there's all sorts of information in a signal. A TV signal, whether it's a movie being transmitted on television or a voice signal or a data communications, there is always so much stuff there that is unnecessary. And what conversion from the time domain to the frequency domain does is allow us to remove it. And just the Fourier Transform alone What's that going to do for us if we take stuff out of here and we don't need to transmit?
Simplifies it.
It's going to narrow the bandwidth. Well done. And the narrower the bandwidth of the signal we have, the less noise, and the more efficient it is. Do you remember, or do you remember, do you know MP3s? I remember I went to see a friend on the New South Wales Central Coast as a visit, and he gave me 2 CDs, and it had on it every song of the Beatles that ever played. And when he gave it, I said, oh, I listened to it, and it sounded really good. How did they do that? I mean, you go and buy a music CD in a music store, you get 8 songs on it. Suddenly you can put 180 songs on it. How did they do that? I asked, and I kept asking, until I eventually found out myself that the Fourier Transform had been applied to the music on the CD and the artifacts removed, and that's how you get MP3 compression. So you can see this Fourier thing is pretty damn good, isn't it? JPEG images, JPEG images, the same thing. The Fourier Transform is applied to them, and just applying the Fourier Transform and removing the artifacts, the artifacts and the information within the music or data or picture or whatever it is that we just don't need. They don't add anything to the intelligence of the information that you're looking at. So if you can remove all that rubbish, look at MP3s. Look how big MP3s are. Like I said, you get 150 on a CD. They gave me 2 with every song the Beatles play.
Is that also called compression?
It is called compression. It's called Fourier compression. But there are other types of compression as well, but nothing comes close to Fourier compression. I just want to make sure you've got this quote. And I'll go back to the BPSK again. This is a graphical way of representing the signal. And we're going to represent BPSK where you have a sine wave, and it's one phase for a 0, and it's another phase, 180 degrees out of phase, for the A. So that could be a 0, this could be a 1, I'll do them the same colour, that's this phase. And that's that phase. So all we do with phase shift keying, binary phase shift keying, and radio amateurs use that for keyboard to keyboard chat. They just sit there on their keyboards, they don't talk, they just type. And it transmits the data, in this form. One phase for a 1, other phase for an O, 180 degrees out of path. But notice with PSK, the symbols are on the circumference. So if you go to 4 PSK, 8 PSK, 10 PSK, the circumference starts to fill up really quick. Because with PSK, it's just the phase that is changing. With quam, quadrature amplitude modulation, the symbols are represented by 2 characteristics of the sine wave. One is the amplitude, and the other is the phase. You'll never have to do that, and you'll never have to do a a fast Fourier transform yourself, people who do have to do it don't really do it because it's usually done with software, and most modern software packages have got a Fourier library in them. You know, so the programmer doesn't have to write all the code over and over again. He knows that the software, I program in Pascal, and Pascal has a Fourier library. You might have noticed that the spectrum analyzers and oscilloscopes have really dropped an enormous amount in price. I can remember when the cheapest spectrum analyzer was $18,000. That was a cheapie. Now you can get an oscilloscope. Probably $1,500. You get a pretty good oscilloscope today, and it's an oscilloscope. So this is time. And this is amplitude. Most modern oscilloscopes have a switch. You throw the switch and it inserts a Fourier transform into the oscilloscope, and you have a spectrum analyzer. And you throw your little, wherever it is, your Fourier switch, and now you end up with frequency. And amplitude. So all of our TV pictures, all of our TV signals use QAM, and that's one of the reasons why we don't get the interference today like we used to. I don't know if any of you were active radio amateurs back in the 70s and 80s. But TV interference was just on all the time. You know, it was amateur radio operators hated it because they knew it wasn't them, because their TV wasn't interfered with, so it's not me. And so the radio inspector was there all the time, sorting you out with interference, talking to the neighbour. That's gone. Technology has just made our hobby a lot better in terms of interference. All because of QAM method of modulating and the Fourier transform. And that's all you need to know for your advanced syllabus. Any questions at all? Double Dutch, did you follow what I said? Good.
That Fourier name, is that the same guy as made Fourier analysis?
Yes. What was his name? Fourier was his name. He developed the Fourier transform back in 1822, but it was just a mathematical odyssey. There's nothing you could do with it until, what, nearly 90 years later, Cooley in Kentucky wrote an algorithm to use the fast Fourier transform. Now it's in all of our electronic equipment. You buy an oscilloscope today, you've got an analyzer, spectrum analyzer as well because of the Fourier transform. Oh, that's one thing I forgot to mention, just one thing. The Fourier transform and QAM alone is not quite enough because all of these things, when you're transmitting and receiving QAM, this has to be done in real time. As I'm speaking into the microphone, the processor in the radio or whatever has to be converting it in real time to QAM. So when we had these motions that I had up here, we started at 2,400 watts. I think we went up to 48K or something, and then we went to ADSL. Why didn't they just start up here? They're going through all this evolution because the processing power of the processors used in modems weren't fast enough. The processing power just, we knew straight away, I didn't know straight away how come we can get such high speeds over a copper pair. But they couldn't make the jump from here to ADSL because the the little computer inside the modem couldn't compute and do the conversions fast enough. Then 2 or 3 years down the track, they brought out a faster modem. And 2 or 3 down the track, brought out another one. All right, that's it. I'm done. Thank you very much. Let's go to the talk next week. Matt?
What on?
You name it.
Sausages.
You name it.
We'll see.
Thanks very much, guys.
That's great. Thank you very much.
Thank you.
Thank you.